it start actually. Let me come here and let's share the screen. Let's share the screen also. Let's start the class. Let me connect my. Okay. Okay. Okay, let's start the class today. Okay, hello everyone, welcome to the class. And now let's check the recording is happening. Yeah, recording is going on. So we can start the class. So last class we discussed some overview and a glance of fabrication, right? So we understood some couple of things of fabrication, what is fabrication, some couple of small things we try to study last class. Okay. So today we will be looking in depth of those things regarding the fabrication and all sorts of things. We discussed all these points in last class. We discussed all these points in last class. We tried to recall that this will be our agenda for overall thing. So we will start from the wafer creation. Okay. The what is actually the chip making is. What is actually the chip making is. You should know the chip making process flow. The chip making process flow how? Layout. As a layout engineer, when you are as a layout engineer working, okay, you guys are making layouts, you are making circuit designer guys are making the circuits, okay, and you guys are making the layout like this kind of, okay, like this connections, like this these kinds of layout
Can't
you
see
guys
your
are making in the. Hello, Crystal,
can't see your screen, sir.
can you repeat again? I'm unable to listen, hear your voice.
We can't see your screen, sir.
Is
It's
it?
visible. It's visible.
Can you please share it again, sir? It is not
Yeah,
visible for me.
yeah. Now it is okay. Now it is okay.
No, sir.
Nageshwar,
No, sir. No.
is it same for other guys also?
No, it's visible from my side, sir.
Can you rejoin Nageshwar once?
Visible, sir.
Yes, sir. Sure, sir.
That will be better, I think. Okay, so you guys are making. Okay, let me admit him. Can you view the screen, Nageshwar?
Yes, sir. Continue, sir. Thank you.
Okay, so you guys are making suppose layout, suppose like Nilani, Nageshwar. You guys made. You guys all Naga Ganesh, then Akila, all guys made one layout in the system computer. Then this layout format is sent as a masks. Okay, mask to the fabrication plant. Okay, in the fabrication plant, they will first do the creation of the wafer, then this crystal growth is there, then the wafer is formed, then some couple of process is there like ion implantation, chemicals, etching, then etching is there, oxidation, then the diffusion, and then CVD process. This whole step, if you see this whole box, if you see this whole box, if you see this whole part, it is called as fabrication. This whole thing is called a fabrication. One, two, three, four, five, and some couple of steps are there. So this is whole thing is called a fabrication. And then this part comes out with this kind of, earlier it is plain. Now the step, now the materials are on the chips are made. It is called processed wafer. Then it is cut down into several pieces. Then this actual chip comes out. So this is then packaging is done. It is go to packaging. So this is the actual flow of a whole fabrication. If the interviewer asks you, can you explain the flow of fabrication? You have to explain in this sequence. First layout, then from layout mask is created. In the other side, wafer is created from the crystal growth. Then on that substrate, all things are created. Like as I told yesterday, After coming into this box part, you have to explain those part which I told you yesterday, how to form NVL, how to form metallization. These all things will be there under this process, like oxidation process, etching process, ion implantation, diffusion, because NVL is created using ion implantation. Okay, so you have to tell for NVL, we have to use ion implantation to make the NVL. Then chemical CVD process, then diffusion, then some polishing will be there. Then final it will come. So you have to explain this whole hierarchy, including those points which I told yesterday class. Okay, then you only will able to properly explain the whole layout thing. Okay, so this is the flow of complete flow. This is okay. After this is the just only a flow. Now starts the actual thing. Now come the crystal growth. Layout, you know, layout you have studied. Layout, you means you will be studying in detail how to design the things, design files, that you know. That's the different thing. Other part of the fabrication is this one also. For how this kind of circular disc is made, you have to tell. This is called growing the crystal ingot. Ingot means, if you have seen like a cylindrical shape, like this is suppose let me tell you, suppose this is a cylindrical shape. Okay, so this is suppose a cylindrical shape. Okay, suppose this is a cylindrical shape, this kind of. Okay, okay, actually the wafer looks kind of this. It looks like this. Okay, you have to just, and from their side also it will be like this. The blades will come and it will cut these things. Okay, it will cut these wafers. So after being cut into several pieces, you will get this kind of circular wafer. You will get this kind of circular wafer. Okay, so if you see this long thing, this is a silicon crystal. It is called a silicon crystal. This is a silicon crystal actually. Okay, so this is a silicon crystal. It is been cut by machines of nano blade. That is why you get this kind of wafers. Then it is been polished to make the surface smooth. Okay, so this is how silicon crystal looks like. Okay, so now we will tell how this silicon is being made. This is called a ingot. This long thing is called an ingot. Okay, so I will tell how it is being made. So the process of making, the most common technique is the Scrolaski method. The Scrolaski method is being used to make these kinds of ingot or the crystals, big size crystals. Okay, so this is called a Scrolaski method, CZ method. You also it is called, developed by Mitsubishi Material Silicon in 50s. Okay, so this is the example of that one. So length is this one, up to 2 meters, diameter is 200 meter or 8-inch, 12-inch wafers are different upon the wafer size. These are the standard industry size of wafers, are 12-inch to 8-inch, 12-inch. If you have made pizza in your home or you bring it from Domino's, you will see 8-inch and 12-inch pizza is there. So maximum 12-inch. So might be the fabrication guys were inspired from the pizza size, like 8-inch or 12-inch pizza size. They also might have been, that's why they kept 8-inch or 12-inch. Okay, it could be from the diameter from 200 mm to 300 mm. Weight can be 220. It's a heavy thing, so it's a 225 kg. Pulling to take up to 100 hours. Okay, so this is a crystal ingot. Okay, so this is being made using the Scrolaski method. What is Scrolaski method? Now we will get to know. So this is just a image of a silicon. We will get to know this is the process. Scrolaski method is used to make this one. Now we will get to know how it is being made. Now let's come in this part. Okay, Scrolaski method. So Scrolaski method is developed by Mitsubishi in 50s. Crystal orientation is determined by seed orientation. Ingot diameter determined by temperature, orientation, and extraction speed. Okay, so this is a Scrolaski method, which is called a crucible. This is a big sized crucible actually. Okay, in this one, the silicon parts are put on this one. Then it is heated with a high temperature. If you see this part, it is heated on a high temperature. Due to which what happen, if you see the temperature is here is, let me make it colorful. Let me make it colorful. If you see, the temperature is 1420 degrees centigrade, this temperature. Okay, then it is actually, this is the seeding process. This is called a seeding. A thin like structure will be drawn from that, a thicker structure will come out. Okay, so then this is a single crystal silicon. This is a, this, you can see this guy. If you see this guy, it is a single crystal. Here it is also highlighted properly. Then the quartz crucible. So this, you can see this yellow thing. You can see this yellow thing, this circular yellow thing. This is called a quartz crucible. In this one, this kind of wafer is being created. This silicon ingot is created. So it's a water cooled chamber. So it's a kind of a big chamber, size chamber. So a water cooled water is being poured in the side, then heat shields carbon heater is there, so for heating the element, that silicon, and graphite crucible inside that one is a graphite crucible is also there. The one quartz crucible and the graphite crucible, both are inside that one, and crucible supports, then spill train electrodes. So these electrodes to put the current in this one. Okay, so this is the overall structure of a Skrolaski method. So if someone asks you what is a Skrolaski method, explain, please tell this one. This all steps by making one this kind of rough diagram, not to make much detail, just you can make a rough diagram like this kind of, you can make a rough diagram like this kind of, like a cylindrical structure you can make. In this one, just make a this kind of structure. Let me make it for you. And in this one, just make a silicon of this kind of thing. Okay, and then this is a seeding thing, and you will able to, then you will able to tell that this is how the process is done, and this one just put a electrode on this one. Okay, so this is how this actually thing looks like. Then you can just mention this is just ingot, ingot, or the silicon crystal. Then this is the chamber, cham I'm writing here. Then this is called the crucible. Crucible. Then inside this one heater is there, just put one layer of thing and write it heater. Okay, heater is there. So many things can be the not much. So this is maximum can be done in an interview, that you can explain that using this process, then it is being rotated at a high speed, extraction speed. So and the temperature is 1420 degree. You have to mention that one, and then this it is drawn, and this kind of big size, this kind of big sized crystal is being formed. If you go, if you go, I will show you the crystal size also. Let me show you the crystal, this thing. I have the crystal image also. You can see this is how a crystal looks like, this big sized. Okay, so this is the actual image of a crystal. Okay, here also the same image only they have put down. Okay, so this is how a crystal actually looks like properly. Okay, so you have to explain the Skrolaski method in this way, that in Skrolaski method, first step, the materials are poured into the silicon materials are poured into the chamber. The chamber has this kind of specifications. In that one, it has been the ingot, then you have to tell that it is put there, and the ingot, it is called ingot, this thing, this big thing called silicon crystal, or you can say the ingot also. So ingot diameter is determined by temperature, which is this one. Orientation, how orientation, it is x and y. Then the extraction speed, how extraction speed is done, and the seed orientation, the seed orientation is x or y. So this is the seed, this thing is a seed orientation. So if you see the extraction speed, due to which this all parameter, the diameters of the ingot is determined by temperature, orientation, extraction speed. After this one, this kind of crucible is drawn out. The whole method is called Skrolaski's method. Okay, CZ method. After this one, this kind of big size crystal is being drawn. Okay, so this is what a Skrolaski method. After this Skrolaski method, the crystal is being made properly. It has been drawn. It has been inspected by one of the fabrication plant engineer. Okay, or the technician. Then the slicing comes. like in a saw machine, wire saw, a thin wire, like the wire is thinner, more, it is thinner more than your hair also. It is much more, very, very thin. So ingot is cut around and ground down into uniform diameter, like 8 inch or 12 inch, then sliced into wafer of about 1 mm thick. So 1 millimeter thick is very, very thin, that wafers are. So for that one, the wire should be also very thin, more thinner than 1 millimeter. So this is called slicing part. So in this slicing, if you see that this kind of crystal is been cut down into circular sides, so that you can get those wafers to go to the next process. Okay, so anyone asks you what are the wafer sizes, generally you can say 8 inch to 12 inch, or 8 or 12 inch, you can tell. Okay, then come the lapping process. Lapping process is the sliced wafer are mechanically lapped by use of aluminum abrasive material to remove surface roughness. When the crystals is there, when it is cut, there some kind of, when this kind of crystal is cut down, when this kind of crystal is cut down, suppose, okay, this kind of crystal is been cut down, okay, this one. So this crystal, when if you see from sidewards, you will able to see, like let me show you, like suppose crystal is, then you will see some kind of roughness is there, some kind of roughness like structure will be there. It actually should be very, very smooth. For that one, a aluminium abrasive material, lab use the aluminium abrasive material, or you can say the surface is rough, a kind of polishing is done, so to remove the roughness of the surface and to make it smooth. uh, it says that remove surface roughness and damages caused by the saw cuts to improve the flatness of the wafer. See, okay, mm, okay, you are driving a car on a road. Okay, you are driving a car on a road. Okay, let me. Okay, you are driving a car on a road. Okay, and the in the road, if you come to see that some of the, if you see the road from this angle, suppose road is like this, okay, sorry, the road is like this, okay. Okay, the road is like this, smooth. The car will move smoothly. Suppose if the road is now like uneven, like it's a pothole, somewhere bumps are there, then what will happen? The car will not move smooth. So that is the reason the surface, due to the cutting of the wire blades, using the wire blade, the surface has some couple of damages on that one. So small, small damages are there, roughness, ups and downs are there. To improve those things, actually this lapping process, or you can say polishing process, is done to remove this roughness and to make improve a flat surface of make a flat surface. Okay, improve flatness of the wafer, the wafer become flat and smooth, so that it can proceed for the next step of the fabrication part. Okay, so we got to know what is ingot. Okay, ingot is also called as a bowl. It is also called as a boule, bowl. You can also use this term also. Generally, ingot, try to use ingot, because many of the guys will not know this term bowl. So try to use this term ingot, crystal ingot or silicon crystal. Okay, like a cylindrical shape silicon crystal, or you can say ingot. Ingot means, if you try to check, ingot means a cylindrical shape in which has been drawn from a silicon, or it is also termed as a very general a salami shape. It is called a salami shape actually, in which, like if you see chicken salami, or if chicken salami is being cut from this kind of cylindrical shape, if you see in the big shopping mart, you will see bread, in the bread circular salami, a square salami is there, just put on the bread with a cheese and eat. That how it is cut from a big sized cylindrical material, that cylindrical shape, that shape of that salami chicken is like in made in form of a cylindrical, from that it is been cut down. Okay, so this is also that kind of shape from where it is been cut down into this type. So this is called crystal ingot. How it is being made? It is being made using the Skrolaski's method. In the Skrolaski method, these are the steps to be followed. Okay, ingot is there, this is the ingot, the chamber is there, then the crystal is there, heater is there, what carbon heater, what which kind of heater? It is called carbon heater. Okay, then spill tray is there, these all the specifications are there. Then this kind of wafer is being drawn out, and it is been the process consumes a heat of 1420 degrees centigrade. And to make the crystal, the ingot, and to which decides the in what are the parameters deciding the ingot, this this crystals diameter. What is the material used for the crystal diameter? This the diameter actually, that ingot diameter by temperature, orientation, and extraction speed. How the orientation is decided? Orientation is decided by the seed orientation. How this thing is put in direction X or Y. So this is how you have to say. How the scholastic method, the ingot is been made. After this ingot made, it is been sliced down into several small pieces. These small pieces are then again taken down. Okay, these small pieces are being taken down, and then it is being polished properly. It is being smoothly polished, and then this okay, before this polishing, this it is being cut down in a shape of a 8-inch diameter or 12-inch diameter with the 1 mm thick. The wafer size is 1 mm thick using the wire saw machine. But due to cutting time, there are some uneven and roughness surface available in the damage due to the wire saw in the over the wafer. To remove those roughness, we use called lapping process, or polishing process also it is called same. Okay, so to remove the roughness, damage, and the damages caused by the saw cuts, to improve a flatness and uniform floor of the wafer. To Okay, so this is how what is the wafer is till the wafer is being created. Okay, now this wafer will go for the further process of the fabrication. Okay, now this wafer shaping. Now the come the wafer shaping, which is called etch. Mechanical damages induced during the previous process are removed by chemical etching. Some mechanical damages are also there. Okay, so those things are removed by each process. Okay, so after lapping smoothness, some kind of process are removed, remained on the top of the wafer. So those things are removed by the chemical etching process. Okay, after the chemical etching process is done, then finally comes a final polishing technique, polish, a mechanochemical polishing process, or it is called a CMP process also. It is called a CMP, chemical mechanical polishing. It is called CHEMIC, chemical mechanical polishing. It's called chemical mechanical polishing. A mechanochemical polishing improves the flatness of the wafer, making highly flat surface by use of colloidal silica. Okay, so this polishing is done, chemical mechanical process, using the silica to make the surface more smoother and even and uniform, so that the shapes when it is getting fabricated over that one doesn't have any kind of errors due to the wafer's unevenness. Okay, that is the reason this final polishing kind of thing is done. Okay, then this goes to the next step of the fabrication part. Okay, till now any queries there you can ask me. Hello, hello.
No, no, sir.
Is it clear how to make the ingot? What is Krolaski's method? What is lapping? What is like slicing? What is each and what is polish?
Yes, sir.
Okay. Okay, you have to read this PPT again and again so that you get more clear. Okay, one time if I tell you, it might not get inside you, so try to read this PPT and read the video again. Okay, so now the CMOS process at a glance. It's just a small summarized view, defining the area of each and field trenches. So one full lithography sequence per layer mask. These are just a normal process at a glance. Okay, and then beat roughly from a bottom up. So metal to metal one, polysilicon source drain, tubs, wells, and activity. So the process is like this. Okay, first the tubs like whales are created, N whales, P whales, whatever it is. Then the polysilicon part is created. The, the source and drain diffusions are created. Then metal one is done. Then metal two. Then go to the metal three, metal four, metal five. This is the step of the a glance you can say of the CMOS process. Okay, so defining area, active area, each and field trenches, implant well regions. So this is the overall. If you see that this is the overall step hierarchy of the whole CMOS process, and this is the way it is being created. First, whales are created, then polysilicon, then source drain diffusion, then metal one, metal two, metal three, metal four. Like this, it will go. Okay, whatever inside the designs layer. Okay, this is the glance. Now come to the planarization. I think the planar spelling is wrong. So, okay, the planarization, polishing of wafers. Okay, the polishing of the wafers. Let me do one thing. 1 second, please. Okay. Planarization, polishing of the wafers. Okay. So what is the planarization and what is polishing of wafers? We already are that mechano-electrical chemical processing that we told. I told you what is CMP, chemical mechanical process. So liquid carrier with suspended abrasive component, abrasive alumina. You already got to know in the polishing part. Okay. So that abrasive component such as aluminium oxide or silica. So that alumina we told. So this is the polishing chamber where the wafers have been put down here for the polishing. It is called chemical mechanical planarization or the chemical mechanical polishing. Okay. So essential to keep the surface of wafer approximately flat between processing steps. Okay, so this polishing is done. So this CMP is done many times for when drawing the metal part also, or drawing the anvil part also. When the uneven surfaces are done there, so this kind of CMP process will be done multiple times to make the surface smoother, so that it should not create any error in the next step actually. So that is the why the CMP process. CMP process means it is a chemical mechanical process in which like aluminium oxide or silica are there, which is used to polish the wafers to remove the uneven or rough surface over the wafer, which occur due to the making of and cutting down the wafers. So that kind of reason that the CMP process is done. Okay. Now come to the next step, which is called photolithography. So we already tried to understand photolithography yesterday. I told you a IC. So up till here we got to know. 1 second. Like up till here we got to know crystal creation, like step one. 1 second. Okay. We first came to know crystal making. Okay. Silicon or ingot. Okay. Then we came to know cutting. Then we came to know, after cutting, then we came to know the process called lapping. Lapping, then came the etch and polishing. After polishing came planarization. Planarization. After the planarization came, the over each polish done, planarization done. Then came the lithography. Okay, so lithography came. Okay, so this is the first 5 steps of 4 to 5 steps are there in the fabrication part, which is responsible for making itself only the crystal part. Planarization, chemical polishing, making the crystal. Then it comes to the lithography part. So where the light will fall and it will create the surface there. Okay, it will create the surface there. I don't know if you guys have tried, like, can you tell me who have tried PC fabrication in your college life? Can anyone tell me anyone has tried that PCB fabrication? Who all have tried? Can you tell me? That's a very easy example to understand. Nilani, Nanda, Ganesh, Nageshwar, anyone tried this PCB fabrication? Okay, Nilani. Yeah, tell
Sir,
Ganesh.
didn't hear you, sir. Yes.
Like you tried, you all have tried in your college like PCB fabrication?
No, sir. No, sir.
If you have seen in the YouTube, might have saw that thing. Some guy is designing one kind of, suppose, like one kind of circuit he has designed in a, suppose this is a PCB board. He has designed in a CAD tool
Hmm.
this kinds of like design he made. Okay, so this kind of design might he have made like this. Then like these kinds of design he has made here, then okay, so like couple of things are there, so these kinds of connections. Okay, so this, so after this has been, there is a copper board is there. Okay, so copper board is there. In that one, he just put this he just print this particular design in a paper, on a photo paper. Either he will put that photo paper over this one, this board, copper board, and he will just put a like cloth iron is there, na, cloth iron is there, he will just put that cloth iron on top of this, and he will rub for some time. The design will get transferred to this clad board. You will see that design will be over this clad board, this copper board, what you can see. And after that one, there is a chemical called FeCl3, ferric chloride. Okay, FeCl3. If you put this board on a FeCl3, a powder comes, just put that in a water and shake it, and then put that board in that one, try shaking it for like 5-10 minutes. You will see that designs where it was there, na, design is a ink, it's the ink material over printed over paper. That ink got transferred to this ink material. Wherever the ink material is there, the copper is hidden. That copper is it, that will not come into contact with the FeCl3. Okay, but the wherever the copper is there, Fe plus FeCl3, what it will do, it will just try to remove that copper. Okay, Fe FeCl3, what it will do, it will just try to remove that area of copper, and the remaining part where the ink is there, that remain part copper will be there. So it's a very easy step of a fabrication. So this it can be also done with a one step ahead. Like I can tell you that iron is there, na, remove that iron, put this paper here, you make a design this ink, print this thing on a transparent plastic paper using a laser printer, put it over a clad copper board, and put a UV light on top of that one. You will see that UV light is there. The UV light is also used in lithography also, that this image will be transferred to the board. Then you put in FeCl3, you will get the same result. So this is a very, very useful technique. If you guys get a time, go to the YouTube and type there uh, PCB fabrication using FeCl3. You will get to know that thing, how a basic fabrication can be done. It's an advanced fabrication though. It's a very basic fabrication. Like you guys have done soldering in the college.
Yes, sir.
What is soldering? Soldering is kind of a fabrication only you are doing. Okay, so you are just connecting those things using a solder wire, using a soldering iron and a solder wire. You are just making a connection. That's a very easy example of a fabrication. That's a very easy, but very, very basic of a fabrication. If I divide this thing in a three part, so part one is that soldering one. Okay, soldering one. Then two will be this design part, PCB fabrication. PCB fab. Actually this PCB fabrication in the industry is done by CNC machines, but this is a very home-based technique to make a PCB fabrication. But this you can make a single layer PCB. It's a very useful to be done. Okay, and third, if you come to see, which is our giant guy, which is called CMOS fabrication. From this only easiest step, this all thing bigs have been derived. So it has much more advanced techniques, much more precision, much more accuracy in CMOS. Okay, because the size of the CMOS are in nanometer. This can be seen in naked eye. This cannot be seen in naked eye. Okay, so this is how a fabrication thing works. If you get a time, just go and type in a YouTube how to do PCB fabrication using FECL3. If you get a chance, make one. Don't do anything. Order a clad board. It's called copper clad board from Amazon. Purchase a FECL3 over the Amazon. Bring it. Just take a marker pen. Okay, and try to draw one circuit here and put that in FECL and try to shake it. You will see here that fabrication has been done. Or if you write your name with a marker with a bold letter and just fabricate that, go to put in the FECL3, you will see your name has been come there. The rest part where copper was there, it has got removed. So this is how actually a small, very easy fabrication example can be done. Okay, you can try this one at home if you get a time. Okay, so this is actually lithography is also kind of that one, and UV light, what it is been done there. A IC consists of several layers of material that are manufactured and successive steps. Like photo plus litho, light and stone plus graphy writing. So writing stone with light. It's a very commentable line. It has been there. Writing stone with light. Okay. Photo means light, litho means stone, graphy means writing. Writing stone, okay, with light. Okay. So photolithography is used to selectively process the layers where 2D mask geometry is copied on the surface. A 2D mask geometry which is copied on the surface over the wafer. That is how a lithography actually works. Okay. I will show you some couple of images of lithography, how lithography, all these things are done properly. If you come here and try to see, if you see in this part, some other concepts are there like oxidation, then what I can say, ion implantation, diffusion. These are concepts there. I will tell you all those concepts in other are going forward. So if you see this one, if you see this design, it's a zoomed image with a microscope of a chip. It has been, you can see here, it has been clearly mentioned that many things are actually inside this particular thin chip, so that you can, it's looking at 3D shape. You can see the 3D shape activity. So this is how lithography can be done in the overall, if you can see in the chip. Okay, so this is the photography step. So if you come to this photolithography now, the photolithography process, how it is done. Okay, if you see here, so oxide growth is done. Oxide growth, that thing is done. If you see here, photoresist removal, which is called ashing. I told you yesterday, photo removal, photoresist removal, which is also called ashing technique. Okay, so it is been implanted with the oxide growth and then present in the form of photoresist coating. A photoresist material is put on the top of the whole this wafer, so that the area which is, it is very sensitive to light, photoresist material. The area which is comes under the light will get softened. With the area which is not inside the light, it will not get soft. It will become hard only. Then the chemical will pour on that one. It will remove the soft part. So if you see the optical mask, so this is a mask actually here. Okay. So if you put this mask thing here, you will see that light is passing through the mask and getting fabricated over that particular part. It is called stepper exposure. Then this is taken into this one, the photoresist development. The photoresist development, it is being removed properly using an acid etch. The material is removed. Then in a spin coater, this is called a spin coater. In the spin coater, it is been rinsed and dried thoroughly. This acid is removed properly. Then this ion implantation and these things and this plasma etching things are done again. These steps are being moved on for the different layer process using the different mask. After the final done, it is been taken out to the cutting like, because when the wafer is being created with the designs, you will see some couples of designs are there. You will see some couples of designs are there. You have to cut these designs out. You have to cut these designs out. Okay. You have to cut, because if you see, if there is a 100 design, in the 100 design, 80 designs will be used. Other 20 will be get thrown out in the dustbin, because by the time of cutting, some get cut from the between itself only. I mean, that is not working anymore. And not the corrections are not there. So which are cutted like very smoothly, very accurately, those things are considered as a proper quality, and other things are thrown out in a dustbin. Okay. So these quality things are being taken for carry forwarded, and then further process like packaging and interconnects are made over this particular block. When the blocks are cut down, it's a shape of a this much small shape is there. So in this shape, you will able to see a small fabrication thing is there. Okay. So this is how a fabrication step of a photolithography is done. So now you can go, you can check that one. So whatever we are discussing yesterday, we will go to there. So these are the step by step how substrate is growth, how this is done. So before that one, you have to get to know overall process. What are the process we have to understand? What are the process consist each of the steps? This all thing you to get to know. Okay. So these are the each individual process, how this each layer is being created properly. So how this each layer is being created properly over this material, so that we can carry forward them. Okay. So this is actually how the crystal growth is made, how the crystal is made, actually ingot is made. We today came to know what is the complete chip making process. Then what is the crystal ingot? What is its diameter? 8-inch and 12-inch industry standard. Then we came to the Scrolansky method. What is Scrolansky method? What is the temperature? What is the ingot's diameter is defined as temperature, orientation, extraction speed, and seed for the orientation. Okay, so what now after that, wafer shaping, what we like slicing and lapping, we understood. Then etching and polishing is also we get to know how to make these all things. Then we came across the glance of our CMOS process whole thing, how the step by step it is done for the tops like N-well, active areas, P-well, these things are done. Then the polysilicon is made. Then source and drain oxide using the diffusion method is done. Then it comes the metal one layer, metal two layer, the metallization process that is called. It will come, these are the steps how it is being carried forwarded in the photolithography. Okay. Then comes the planarization. What is planarization and CMP, chemical mechanical planarization or polishing to make the surface smooth using the silica and aluminum dioxide. This is the liquid carrier actually for the chemical mechanical polishing, CMP or polish planarization process. Then we came to know what is photolithography. Photolithography, let me tell you one point. Photolithography is nothing but a simple light beam, a laser light beam coming from this part, very thin light beam. Okay. A mask is present on this part, a mask is present on this top part, if you see here, you will see some designs are there. Okay, suppose this is a design. It is passing through, this light will pass through this design only. After the design, light is passing through this design. Okay, the wafer is put below over this kind of plate is there, in which the wafer is put below. Okay, the light is passing, the wafer is coated with a photoresist material. Now let me put a photoresist material on top of this one. Okay, let me put a photoresist material on top of this one. Okay, let me put a photoresist material on top of this is the red one, is the wafer in which the photoresist proper material is being given, so that the part where the light falls, if the whole thing is covered with a photoresist. Okay, the whole thing is covered properly with a photoresist material. And then what we did here is, we put the light, pass the light from this part, and then what happens, the light falls on this part and it creates a shape like this. Because the shape is kind of like this, it will create a shape for us like this. Okay, in the shape where this part is there, you will see when the shape falls on that part actually, the photoresist at this part, this inside this rectangle, will be softened, will be soft in compared to the outside things. Okay, will compare to the outside thing, the internal the in the photo inside this one will be much more softer quality. Now when the acid etching is poured over this one, which pour over this one, which is called actually ashing or the photoresist removal. This one, you will see this part, if you see this is a softened part, it will automatically get reacted with the acid and it will get out of this one. And then you will come to see the final wafer you will get to see is like this kind of thing. Okay, you will see the final wafer. If you see the final wafer like this, you will get to see a complete structure like this have been there. Okay, let me show you a complete structure in like this is there on the top of this wafer properly. And other part is normal. Again, we will do the same process. We will create a other shape also at this level or other part, any part. So if you see this part is softened, this part is removed using the ashing technique. This soft part got removed. Then we remove the other photo etch using the HF, hydrofluoric acid, the hardened part. This is the soft part, this is the hard part. Okay, so hard part will remove the hydrofluoric acid. This is also will remove hydrofluoric acid, but the concentration will be different for both the cases. Then after that one, you will see this whole thing, this shape is on this one. Okay, so this shape is responsible for its actual support might be a kind of a design shape, like any device PMOS or NMOS, any kind of shape it can be. This shape has been got fabricated over this wafer. Okay, so this is how a lithography works. So this is a lithography actually, the lithography machine. The lithography machines are created by ASML is there, Lam Research are there, many big companies. The ASML is one of the big giant company in creating this such kind of lithography machines. Okay, so this light has a wavelength of 130 nanometer, which is currently new. As I know, 130 nanometer is the new one. Still, I will check once and I will let you know with the minimum wavelength actually in the industry standard working. I think, as I know, 130 is the EUV. It is called EUV method. Okay, which is TSMC is currently using EUV, and some is the alternate name is also called UV plus. UV plus also is being used. So this method is being used. This is called the lighting. This is called a that lithography light making process. This light is fall on this one and to create this kind of wafer. Okay, so this is what the lithography we try to understand. Okay, so this is the that pictorial image of the photolithography process chain, how the shapes are done properly, so that the whole wafer can be made properly. Okay, so this is the overall scenario of creating the crystal, how to make the wafer, how to do the planarization, how to do the etching, then what is photolithography and what is the photolithography means cycle. Then we will go to the next part, which is how to create each and every shape in which ion implantation, diffusion, metallization, oxidation, these all things will come across, because each shape, for making an N well, you need ion implantation. For making a source and drain, you need diffusion method. So these kind of methods will take care for before that. What is ion implantation? What is diffusion? I will tell you properly. So this is a thing of the how up till here crystal is created, how the vapor is created. These all things actually the normal overall scenario of the lithography process. Then what is lithography? Then we will come to each and every shape. Like we will consider a inverter first. We will consider a inverter. Okay, we will consider a inverter, which we will try to will see how it is being fabricated. Okay, so how the steps of fabrication in a cross sectional part of this cross sectional part. Okay, what is the this is okay, one second. In this cross sectional part, okay, we will try to see like this kind of doping things, this kind of things. Okay, this kind of things we will try to see how this is been fabricated over a particular substrate p sub. We will try to see these all things. Then we will get to know what is this kind of shapes, how it is been fabricated in each of the layers, what are the techniques for fabricating those kinds of layers, actually how these kinds of trench is created, what is this n plus and n plus or n minus regions. Okay, so we'll get to know why n plus only or why n minus only, not why only n. We'll get to know like which is why less doping concentration. Like in if you come across the excuse me, if you come across the mind, if you see even see that n plus n minus is written, if it is minus, then the it is lightly doped. If it is a plus, it is a highly doped. Okay, so so actually in the industry, n minus or n is only used rather than the n plus. Okay, highly doped is less used, lightly doped is more highly used. That's the reason you will see it's a n minus or n, that kind of thing you will come across. Okay, so these are all the things of the fabrication steps. So now if you have any question, you can ask me. Is there any question regarding these things? You can ask me. Hello.
No, sir.
Hello.
No, sir.
Is it clear to you?
Yes, sir.
Okay. So this is how we actually understand the whole fabrication steps. Okay. So are you all trying that inverter, that say decoder design?
Yes, sir.
Okay. So what is today? I think today is Wednesday. Tomorrow, I think it is you that's deadline is right.
Yes, sir.
Will you be able to complete that one?
Yes, sir.
Yes, sir.
Oh, okay, sure. Okay, then uh, today's session is up till this much only. We will try to we'll continue the session again from tomorrow regarding the other further steps of the fabrication, how the fabrication is done, how the everything is taken care. Okay.
Okay, sir.
Is the class going good for you all guys, or any issue you are facing? Hello.
Fine for myself.
Okay, Nanda, you, Nilani. Okay, then we can end up the session today here. So we will meet again tomorrow. Okay, then, guys, and good night and bye. Okay. Okay, then everyone, good night.